In pulse amplitude modulation, amplitude of the pulse train is varied, width of the pulse train is varied, frequency of the pulse train is varied, none of the above. So in pulse amplitude modulation, amplitude of the pulse train is varied. Therefore, option A is correct. Pulse time modulation, PTM, includes pulse width modulation, pulse position modulation, pulse amplitude modulation, both A and B. So pulse time modulation means, so it is a combination of pulse width and pulse position modulation. That means both options A and B are correct. So option B is correct. The drawback of using PAM method is amplitude of carrier is constant, varying amplitude of carrier varies the peak power required for transmission. So this is correct. So varying amplitude of carrier varies the peak power required for transmission. So this is one drawback. The amplitude of carrier is not constant in PAM. And due to varying amplitude of carrier, it is difficult to remove noise at the receiver. So this is also correct. So because the amplitude is varied, it is difficult to remove the noise at the receiver. So options B and C are correct. Therefore, option D is both B and C is correct. Next question. The process of converting the analog sample into discrete form is called. So the analog sample is converted into discrete form by means of quantization. So just now we have discussed about the quantization process. So the quantization, that is option C, is correct. The modulation techniques used to convert analog signal into digital signal are pulse code modulation, delta modulation, adaptive delta modulation, all of the above. So pulse digital modulation schemes are used to convert the analog signals into digital signals. So in the last session we have discussed about what are the different types of pulse digital modulation schemes. So those are pulse code modulation, delta modulation, adaptive delta modulation. All the three are pulse digital modulation schemes which are going to convert the analog signal into digital signal. Therefore, all of the above is correct. Option D is correct. An analog voltage in the range 0 to 8 volts is divided into 16 equal intervals for conversion to 4-bit digital output. The maximum quantization error in volts is. So the dynamic range of the modulating signal is 0 to 8 volts, which is divided into 16 equal intervals. That means the number of levels are 16. So if there are 16 number of levels, then each sample is represented by means of 4 bits, because 16 can be represented as 2 to the power of 4. So it was given already for conversion to a 4-bit digital output. And the maximum quantization error. So the maximum quantization error is S by 2, because in quantization, the maximum quantization error is S by 2. So the quantization error is less than or equals to S by 2. So for this one, first we have to calculate the step size. So step size can be calculated from the knowledge of dynamic range and the number of levels. So VH minus VL by M indicates the step size. So S is equals to 8 minus 0 by 16. 8 by 16, which is equals to 1 by 2, 0.5 volts. The step size is 0.5 volts. But the maximum quantization error we have to calculate. The maximum quantization error is equals to S by 2. Therefore 0.5 by 2, which is equals to 0.25. So 0.25 is the correct answer. The line code that has 0 DC component for pulse transmission of random binary data is. So the line code which is having 0 DC component is alternative mark inversion or pseudo ternary code, because the one is represented by, alternatively represented by positive and negative pulses of half symbol wide. So therefore there will be a cancellation. So the total DC component becomes 0. So in alternative mark inversion, the DC component for pulse transmission of random binary data is 0. 0 DC component will be there. The characteristic of compressor in Mueller compounding are, so in Mueller compounding, it is continuous in nature. It is continuous in nature. So option A is correct. The bitrate required to digitize the human voice, assuming human voice frequencies to be in the range 0 to 4000 Hz and number of bits per sample to be 8 is. So we need to find out the bits per sample, bit rate. So the given data is the human voice contains frequencies from 0 to 4000 Hz. That means the maximum frequency component is 4000 Hz. So FM is equals to 4000 Hz. Therefore, the sampling frequency is, that is Nyquist rate is twice that of the maximum frequency, which is equals to 2 into 4000. That is 8000 samples per second. And bit rate is given by sampling rate into number of bits per sample. So bit rate, as we have discussed, bit rate is equals to sampling rate, means it is a baud rate, into number of bits per sample. So the number of bits per sample is given as 8. Therefore, the sampling rate is 8000. The number of bits are 8. So 64,000 bits per second. So which can be represented as 64 kilobits per second. So option B is correct. In uniform quantization process, the step size remains the same. Right? This is correct. In the uniform quantization process, the step size remains the same. And step size varies according to the values of the input signal. So the step size is constant. So it will not be varied with respect to the input signal. And the quantizer has linear characteristics. So this option is also correct. Therefore, both A and C are correct. Therefore, option B is correct option. The format in which the positive half interval pulse is followed by a negative half interval pulse for transmission of 1 is. So as from our previous discussion, the Manchester format basically comprises with a positive half interval pulse is followed by negative half interval pulse for transmission of 1 and negative half interval pulse followed by positive half interval pulse by symbol 0. Therefore, Manchester, it is a Manchester signaling format. Option C is correct. In pulse time modulation, amplitude of the carrier is constant. Position or width of the carrier varies with the modulating signal. Pulse width modulation and pulse position modulation are the types of pulse time modulation. So in pulse time modulation means pulse position, pulse time modulation means pulse position and pulse width modulation are combiningly known as pulse time modulation. So here in both the cases the amplitude is constant. So option A is correct and position or width of the carrier varies with modulating signal since it is pulse width modulation and pulse position modulation. Therefore option B is also correct. And pulse width modulation, pulse position modulations are the types of PTM. So that is also correct. So all the three options are correct. So D option, all the above is correct answer. In pulse width modulation, synchronization is not required between transmitter and receiver. Amplitude of the carrier pulse is varied. Instantaneous power at the transmitter is constant. None of the above. So in pulse width modulation, synchronization is not required between transmitter and receiver since the position is constant. The amplitude of the carrier pulse is varied. So in pulse width modulation, amplitude is constant. But since the width is varied, the instantaneous power at the transmitter is not constant. Therefore, option A is correct. The compressor characteristics of ALA compounding are piecewise mode of linear segments for low input levels, logarithmic segment for high input levels, both A and B, none of them. So we have seen the characteristics of ALA compounding. So piecewise mode of linear segments for low input levels is correct, and also logarithmic segment for high input levels. This is also correct. So both A and B, that is option C, is correct. Non-uniform quantization can be achieved by. So non-uniform quantization can be achieved by compounding, computing, none of them. So compounding is a technique which is used to produce the non-uniform quantization. Because non-uniform quantization directly is not possible since the signal levels are not known in advance. So that's why the non-uniform quantization can be achieved by means of a technique which is defined as compounding, which is a combination of compression and expansion. So in pulse position modulation, the drawbacks are synchronization is required between transmitter and the receiver, width is not constant, both A and B. In pulse position modulation, synchronization is required between transmitter and receiver. It is correct. This is the drawback with pulse position modulation. Width is not constant. In pulse position modulation, width is constant. So B is wrong, and both A and B is also wrong. None of the above is also wrong. So option A is correct option. Synchronization is required between transmitter and receiver because of the position is not constant. An analog signal is band limited to 4 kHz sampled at the Nyquist rate, and the 4 sample levels are assumed to be independent and equally probable. If we transmit 2 quantized samples per second, the information rate is. So the signal is band limited to 4 kHz means FM is given by 4 kHz. Sampled at the Nyquist rate. Sampled at the Nyquist rate means Nyquist rate is 2 FM. Therefore, 2 into 4 kHz, which is equals to 8 kHz. And 4 sample levels are assumed to be independent and equally probable. So the number of levels are given by 4. Therefore, these 4 levels can be expressed as 2 to the power of n, 2 to the power of n, or n is equals to 2. So since this 4 can be expressed as 2 to the power of 2 square, so n is equals to 2. So 2 bits are required to represent each of this level. So the number of bits is equals to 2. And each sample requires 2 bits, and 2 samples per second are transmitted. Each sample requires 2 bits and 2 samples per second are transmitted. So 2 samples per second. Therefore, the number of bits per second are 2 into 2, which is equals to 4 bits per second. Therefore, option D is correct. Next is, in polar return to 0 format coding, symbol 0 is represented by. So polar means it comprises with both positive and negative pulses. Return to 0 means they are half symbol wide. Please keep it in mind this. And symbol 0 is represented by, in polar return to 0, symbol 0 is represented by a negative voltage of constant amplitude and half symbol wide. So therefore, if you see the options, 0 voltage, negative voltage, and pulse is transmitted for half the duration. So 0 is represented by negative voltage, correct, and pulse is transmitted for half the duration. So this is also correct. So both A, B and C are correct. So option D is correct answer. In unipolar return to 0 format, the waveform has 0 value for symbol 0. So whenever return to 0 format comes and unipolar, so unipolar means only one polarity will be there. So in that particular case, 0 is represented by 0 value. The waveform has A volts for symbol 1. So symbol 1 is represented by means of some positive voltage. The waveform has positive and negative values for 1 and 0 symbol respectively. So option C is wrong. And unipolar return to 0 means The waveform has 0 value for symbol 0 and the waveform has A volts for symbol 1. Therefore, both A and B are correct. So, option D is right. And polar coding is a technique in which 1 is transmitted by a positive pulse and 0 is transmitted by a negative pulse. So, polar means two levels. So, positive level and negative level to represent 1 and 0 respectively. So, option A is correct. 1 is transmitted by a positive pulse and 0 is transmitted by 0 volts. So, this is unipolar. So, if 0 is transmitted by 0 volts, this is unipolar. C is both A and B. So, B and C options and D option is not correct. So, option A is correct. The polarities in non-return to zero format use complete pulse duration, half duration, both positive as well as negative value. Each pulse is used for twice the duration. So, the polarities in non-return to zero format. So, non-return to zero format means the complete pulse duration. And return to zero format means half the duration the pulse will exist. Therefore, option A is correct. The format in which the positive half interval pulse is followed by a negative half interval pulse for transmission of one answer. So in Manchester code, actually a positive half interval pulse followed by negative half interval to represent 1, and negative pulse in negative interval followed by positive half interval by means of 0. So Manchester format. The maximum synchronizing capability in coding techniques is present in. So the maximum synchronizing capability is in the Manchester format. This is one of the important characteristic of Manchester code, maximum synchronizing capability. So because of 1 is represented by positive followed by negative and 0 is represented by negative followed by positive. The advantage of using Manchester format of coding is, so Manchester format is, the advantage of Manchester coding is, it suppresses the DC component. So this is one advantage. Polarity sense at the receiver. Noise immunity, none of them. So option A is correct, suppress the DC component. Alternate mark inversion is also known as alternate mark inversion. So which is having 3 different signal levels. So it is also known as pseudo ternary coding. So option A is correct. Compounding is used in the case of signals having uniform amplitude distribution, having the large peak-to-peak amplitude but small wedge power, having a large peak at high amplitude levels in their amplitude probability density function with large wedge powers. So compounding is used in the case of having large peak at high amplitude levels in their amplitude probability density function. So because of the large variations of the signals, we are using the compounding. So that the signals with the signals of strong amplitudes are compressed and the signals of weak amplitudes are expanded. Therefore, option C is correct. 4 independent messages have bandwidths of 100, 100, 200 and 400 Hz respectively. Each is sampled at the Nyquist rate and the samples are time division multiplexed and transmitted. Find the transmitted sample rate in Hertz. So each one has to be in time division multiplexing. Each baseband signal has to be sampled at the Nyquist rate. That means all the 4 has to be sampled at Nyquist rate. Therefore, the Nyquist rate of this particular signal is 200 Hz, and for this signal it is 200 Hz, and for this it is 400 Hz, and for this one it is 800 Hz. That means 2 into 100 plus 100 plus 200 plus 400. That means 1600 Hz. So that gives the sampling rate of the time division multiplexed signal. And 3 analog signals having bandwidths 1200, 600 and 600 Hz are sampled at their respective Nyquist rates, encoded with 12-bit words and time division multiplexer. The bitrate for the multiplexer signal is, so bitrate can be calculated from the number of bits multiplied by the baud rate. Baud rate is nothing but sampling frequency. So here the sampling frequency is, so for each of the signal has to be sampled at least Nyquist rate. Therefore, fs1 plus fs2 plus fs3. fs1 is 1200 into 2 plus fs2 is 600 into 2 plus fs3 is 600 into 2. So 2400, 1200, 1200. So totally 4800 Hz or 4.8 kilohertz. And bitrate is equals to n into fs. So the number of bits per sample are given by 12 bit words. Therefore 12 into 48 into, this is 10 power 3 kilohertz, 48 into 10 power 3. So which is equals to 57.6 kbps. For messages band limited to W, W, 2W and 3W respectively are to be multiplexed using time division multiplexing. The minimum bandwidth required for transmission of this TDM signal is. So again, so each signal has to be sampled at least Nyquist rate. Therefore, fs1 is equals to 2 omega 2W, fs2 is equals to 2W, fs3 is equals to 2 into 2W means 4W, and fs4 is equals to 2 into 3W which is equals to 6W. Therefore, the sampling frequency of the time division multiplexer signal is fs1 plus fs2 plus fs3 plus fs4. That is 2W, 2W, 4W plus 6W which is equals to 14W. And bitrate is given by n times the sampling frequency. And for minimum bandwidth, the number of bits required is equals to 1. For minimum bandwidth, n should be equals to 1. Therefore, RB is equals to 1 into 14W. That is equals to 14W. And minimum bandwidth is equals to half of the bitrate. Minimum bandwidth is half of the bitrate. Therefore, 14W by 2 which is equals to 7W. Therefore, option D is correct. Option D is correct. See, the minimum bandwidth exists when n is equals to 1. And bandwidth, the minimum bandwidth can be RB by 2, half of the bitrate. The temperature at a particular place varies between 14 degrees centigrade and 34 degrees centigrade. For the purpose of transmitting the temperature record of that place using PCM, the record is sampled at an appropriate sampling rate and the samples are quantized. If the error in representation of the samples due to quantization is not to exceed plus or minus 1% of the dynamic range, what is the minimum number of quantization levels that can be used? So here we need to calculate the minimum number of quantization levels. So the dynamic range of the system is given by, so the minimum and maximum range extremities are 14 degree and 34 degree. Therefore, the step size is equals to difference between these two extremities divided by the total number of levels. 34 minus 14 divided by Q. And we know that the quantization error is equals to plus or minus delta by 2 is the representation of any sample. So the maximum quantization error is delta by 2, where delta is the step size which is given by VH minus VL by total number of levels. And here another one is, if the error in representation of the samples due to quantization is not to exceed plus or minus 1% of the dynamic range. So that means delta by 2 is the, if delta by 2 is the maximum quantization error, this delta by 2 is equals to 0.01 into dynamic range. that is 20. 34 minus 14. Okay. So delta by 2, quantization error delta by 2 is equals to 0.01 because it is 1%. That's why it is 1 by 100 into dynamic range. That is 0.01 into 20 degrees. Therefore, so 100 into delta by 2 by 20 is equals to 1 then. So here we are moving this 0.01 here so that it becomes 100 and 20 in the denominator. So from this one, delta by 2 is equals to 20 by 100, which is equals to 1 by 5, and delta is equals to 2 by 5. That means the step size is equals to 2 by 5. The step size is equals to 2 by 5. Therefore, the number of quantization levels Q is equals to 20 by delta. The number of quantization levels Q is equals to 20 by delta, where delta is equals to 2 by 5. Therefore, Q is equals to 50. Therefore, the minimum number of prescribed levels or quantization levels that can be used is 50. So, these are some of the important objective type questions. So today we have gone through the different concepts: time division multiplexing, frequency division multiplexing, and also line coding, different line coding techniques and their characteristics, and the basic concepts of quantization and coding. Please go through all these concepts once again and practice all these problems. And for today, we will close the session. We can close the session now. And thank you.